Welcome to this explainer. Okay, today we're tackling something pretty amazing, how airplane flight physics actually works. I mean, flying isn't just about floating gracefully up there in the clouds. It's actually this epic, ongoing battle of invisible natural forces. Seriously, it's quite literally a high-speed, high-stakes tug-of-war taking place miles above the ground.
Okay, let's dive into this. Picture this. Have you ever been on a road trip, rolled down the window, and stuck your hand outside while speeding down the highway? Yeah, we've all done it. You definitely felt the wind forcefully pushing back against your hand, right? And if you tilt your hand up or down, well, you feel that force completely change. That incredibly familiar everyday sensation, that is actually your very first lesson in the core principles of aerodynamics.
So here's our roadmap for today. First, the car window experiment. Then we'll map out the 4 forces of flight. After that, we'll unpack the vertical battle of weight versus lift, the horizontal battle of drag versus thrust, and finally wrap up with how steering and stability work.
All right, let's jump right into section 1. The car window experiment, your first aerodynamics lesson.
So, when you stick your hand out of that moving car, the resistance you feel is the physical air interacting with a solid object, your hand, and the amount of pushback totally depends on the angle. Now, what's truly mind-blowing here is that this simple, localized physical resistance, it directly mirrors how massive heavy airplanes interact with the sky. I mean, the exact same invisible forces pushing your arm backward or upward on the highway are what allow massive commercial jets to rise, soar through the clouds, and even fly fast enough to break the sound barrier. But, what exactly are these forces?
Which brings us to section 2, the 4 forces of flight, or as I like to call it, the constant battle in the sky.
And this perfectly illustrates the overarching tug-of-war concept that dictates absolutely all flight. So first, we've got our vertical forces, lift fighting against weight. And second, we have our horizontal forces, thrust fighting against drag. For a plane to get off the ground and actually stay there, these 4 forces must work together in absolute delicate harmony.
Let's break these down, starting with section 3, weight versus lift, the vertical battle.
First, just consider the sheer scale of the object we're trying to put into the air here. An airplane is a massive hunk of metal. When you combine the heavy fuselage, the onboard mechanical systems, the equipment, a full payload of passengers or cargo, plus tons of jet fuel, an aircraft can weigh anywhere from a few hundred to a staggering 500,000 kilograms. That is huge, and all of that mass contributes to its overall weight, which is a force constantly, relentlessly being pulled straight downward toward the center of the Earth. So to counteract this immense downward pull of weight, we obviously need an equally impressive upward force, and that upward force is known as lift. The crucial takeaway here is that lift is the real hero of our vertical tug-of-war. It's primarily responsible for keeping an airplane, or really any object, in flight, because without it, that 500,000 kilograms of metal is staying firmly parked on the runway. But how exactly does a heavy airplane generate enough lift to overcome all that weight?
Well, the answer lies in one of human engineering's most ingenious solutions, the aircraft's wings. Specifically, most aircraft's wings utilize a characteristic design called an airfoil. An airfoil is basically a cross-sectional shape featuring a flatter lower surface and a distinctively curved upper surface. This specific, kind of uneven shape is the absolute secret to generating lift. Now, what's really fascinating here is how that airfoil shape literally manipulates the physical air itself as the plane moves. Because of that curved design on top, the air traveling over the upper part of the wing is forced to move faster than the air moving under the flatter bottom. This difference in airspeed creates a completely crucial difference in air pressure. The faster-moving air above the wing results in lower air pressure, while the relatively slower air beneath the wing maintains a higher air pressure.
Let's see how this all builds into actual flight, because it happens in a very precise sequence. Step 1. The aircraft moves through the sky at high speeds. Step 2. That airfoil shape causes the air to move at different speeds over and under the wing. And step 3. This creates a pressure difference. The higher pressure underneath essentially pushes upward against the lower pressure above it. And boom! That pressure difference generates the force of lift. It's this upward push that allows the plane to ascend and stay airborne, successfully fighting off the downward pull of gravity. But, to get that high-speed forward motion that makes lift possible in the first place, we have to look at our second battleground.
Moving on to section 4, drag versus thrust, also known as the horizontal battle.
To really understand this horizontal fight, we need to anchor ourselves in some basic physics. You probably remember Newton's third law of motion from school. For every action, there's an equal and opposite reaction. As an airplane flies, it has to physically push its way through the air. And in response, because of Newton's law, the air fights back, pushing directly against the airplane. This aerodynamic force pushing back is what we call drag. The direction of drag is always opposite to the direction the plane is moving. The source material gives a fantastic analogy here, actually. Imagine you're swimming in a pool. If you paddle slowly, it's pretty easy, right? But the faster you try to swim forward, the more forcefully the water resists your movement. That is drag in action. For an airplane, its speed and its physical shape significantly influence just how much drag it experiences while trying to cut through the sky.
So we've got drag constantly pushing the airplane backward. To overcome this resistance and maintain forward motion, we need our final force, thrust. Thrust is the raw engine power propelling the airplane forward. And here is exactly why this horizontal battle is so critical to everything we've talked about so far. Without thrust, the plane cannot move forward. And, as we just learned with the airfoil, lift cannot be generated without that forward movement. Therefore, without thrust to beat drag, the whole shebang falls apart. Flight would be completely impossible.
So where exactly does thrust come from? Well, an aircraft generates it through its engines. Commercial aircraft are typically powered by massive jet engines that expel air out the back at incredibly high speeds, which then propels the plane forward. And guess what? That is Newton's third-line action yet again. Pushing air backward forces the plane forward. The total amount of thrust a plane can generate really depends on a few key factors: the number of engines on the aircraft, the specific types of engines used, and of course, the throttle setting controlled by the pilot. So, okay, we have lift fighting weight vertically and thrust fighting drag horizontally. How on earth do pilots manage this incredibly intense environment?
That takes us to our final part, Section 5, Steering and Stability, Mastering the Balance.
Pilots actually have an incredible toolkit of components to manage all these warring forces. The tail wings and the rudder are absolutely essential. They help pilots physically control the airplane's direction and stabilize it while it's airborne. Engine positioning plays a massive role too. You've probably noticed that commercial planes usually have their engines located under the wings parallel to the body. But some aircraft, particularly military jets like the Harrier, have engines positioned in a way that allows them to actually adjust the direction of the thrust. This gives them just unbelievable control over these horizontal and vertical forces.
And tying all of this together is a vast array of electrical and mechanical systems on board, working in total harmony. It's this perfect, seamless combination of internal systems and intense physical forces operating tirelessly behind the scenes of every single flight. Honestly, understanding the violence of this aerodynamic tug-of-war makes the engineering feat even more impressive. It's what makes flying not only possible but incredibly safe, allowing us to just sit back, relax, and enjoy the ride.
Which brings us to the end of our explainer today. But I want to leave you with a thought. Next time you're on a flight, looking out the window at 30,000 feet, thinking about this massive metal machine successfully balancing on invisible air, which side of the aerodynamic tug-of-war will you feel the most? Will you notice the powerful thrust pushing you back into your seat on takeoff, or maybe the incredible pressure-defying lift holding you smoothly above the clouds? Think about that next time you take to the sky. Thank you so much for learning with me today, and keep looking up.